which I said I'm going to clarify the subscript r in a minute. And then dx was always in the formula, and then 2 pi always comes out. All right, let's revisit this problem now. So I realize I'm going to rotate it around the y-axis going this way. I'm going to leave it parallel to my axis of rotation, which means I'm going to use shells. I need to know the top function and the bottom function, right? I know those, right? Top one is x, bottom one is x squared. The only other thing I need to know after the top and bottom is what's x here. What does this mean? This means what is the distance from axis of rotation to your rectangle. So what is the distance from the axis of rotation to our rectangle? In this case, it's just x, right? But it's not always just x. Would it be too much to go ahead and just plug things in here? Just go right to this now? Start out with 2 pi. Integral, where to where? 0 to 1. And those limits of integration are controlling our x. So we're looking left and right here. 0 to 1. Distance from the axis of rotation to the rectangle, we just said was x. And then the top function, what is our top function? X. And our bottom function, x squared. Take the difference, and that's it, right?
So if the axis of rotation would have been like -2, then you would have incorporated that onto that x.
Yeah, I'm going to do that now. I'm going to do that after this one, so you can see how shells could have been done with the previous problem we did. All right. I'm curious if we're going to get the same answer. Should we? We should, right? All right, let's try it. This is 2 pi integral 0 to 1 of, I'm going to distribute the x through, x minus x cubed dx, right? Integrate 2 pi 1/3 x cubed minus 1/4 x to the 4th from 0 to 1. Plug in 1, you get 1/3 minus 1/4. Plug in 0, everything's gone. So you get what? 2 pi times, this should be, bless you, 1/12? So you get pi over 6. We get pi over 6. Is that what we would have gotten here? Shall we do it quickly? Antiderivative, pi 1/2 y squared minus 1/3 y cubed from 0 to 1. Plug in 1, what do you get? 1/2 minus 1/3. Plug in 0, what do you get? 0. What's 1/2 minus 1/3? 1/6 times pi, pi over 6. So the fact that they're the same isn't a coincidence. It better be, right? Because the two methods achieve the same result. All right. Now I did one earlier where it wasn't the y-axis. We moved it to the left. Which one was that one? Next was -4. So if we did that with shells, I just want to look at what the difference would be. I'm going to erase this. In our picture, the axis of rotation is now over here, right? -4. What in the formula will change? 2 pi integral a to b xr, and then top minus bottom dx, right? That's the formula? Does the top and bottom function change? Dx doesn't change. 2 pi doesn't change. A and b don't change. The only thing that changes is this. That's the distance from your axis of rotation to your rectangle, which is now not x. What is it? X plus 4. Right? This is 4, that's x. So if we change this, see how easy of an adjustment that is to make? It's just x plus 4 here, and then your top minus the bottom, dx. Whatever that is, you have to FOIL it all out. What was the other one I did? I changed that to plus 8. So when I do, this is plus 8, that's on this side, right? So does your top change? No. Bottom? No. Only thing is your distance from your axis of rotation to your rectangle. So that's the distance from here to here, which isn't x. This is 8, right? Fixed 8. This is x. So from here to here should be 8 minus x. So if I change this, I'm in business. I like shells. Shells is my preference. If I can use it, I'll use it. But some of you may not be sold. So, well, when can you not use it? Oh, that's a good question. Let me show you an example of one where you could not use it. And I'm just going to draw you a picture. I'm not actually going to write functions. But let's say you had this, a parabola like this, along with a parabola like this. And let's say you wanted to take that region and go around the x-axis, okay? You would not do shells, because remember, shells means you're parallel to your axis of rotation. Do you see that if I draw rectangles in here, I don't have, like there's a change in functions and it fails? Do you see that? Yeah. But I would use vertical rectangles and I would have a top and a bottom. I use washers and I'm in business, right? So usually if shells fails, washers will work, and vice versa. If washers fails, shells will work. So I wanted to do a problem that would hopefully sell you on the idea of shells. No, shells can go both ways. Let me give you an example. If I did like this region around the x-axis, oh, whatever. That around the x-axis. You wouldn't want to do washers, because if I do washers, notice that you have the same function. That would be a disaster, right? But if I run my rectangles this way, then I'm running parallel. So you would have your distance from the axis of rotation to your rectangle. Instead of top and bottom, you'd have right and left instead of top and bottom. And this would be our x sub r. It would now be y sub r. So everything would change. I'm not going to give any of these, all right? But you could. I'm just trying to sell you on the idea that you could do it. All right, let's look at this one. Let's take this region. This will be our last example. Let's rotate this region about the y-axis. So it looks like we have some sketching to do. Y equals x. That one I'm happy with. Very happy with. Now what about that negative x squared plus 3x? How could I graph that? It's a parabola, right? Opens down. But I need some more information. How about I find its x-intercepts? Maybe that'll help me graph it. Find the x-intercepts of that. So set it equal to 0. Let's say we factor negative x out. Something like that. Set these equal to 0. You get what? 0 and 3. Something like this. And I need a little more information. How high does that thing go? Not quite sure, right? You could use the vertex formula. You could actually use that formula that you can get the vertex hk, where h is equal to negative b over 2a. This is college algebra. K equals f of h. That's how you find your vertex for a parabola. But I don't really care. Look, it's got to go up, and it's got to come back down like that, right? So I think the region is somewhat obvious. Yeah? Okay. There's my region. I want to wrap it around what? The y-axis. Horizontal, right? Horizontal would be if I want to use washers. Agreed? Washers isn't going to work. Why? Show me where I'm going to have trouble. Yeah, look, this rectangle is fine, right? Blue is there, red is here. This rectangle is fine. Blue is there, red is there. But when I get to the rectangles up here, what happens? I've got the same function, don't I? No good. No good. Can't do it that way. So I've got to do shells. Now let's just verify that when I do shells, as I move that rectangle left and right, am I going to have any issues? The red's always going to be on top? The blue's always on the bottom? So I'm okay with that, right? But I'm running parallel to my axis of rotation, which means shell time, right? What are the things you need to know for shells? Hold on, hold on. Sir, what do you need to know for shells? 3 things. No? Okay. There's a difference between being present and actually being present. So I can't help you if you're asleep. Volume equals 2 pi integral. Okay, so I'll get to the limits of integration in a second because that's going to be a bit of an issue. We need to know x sub r, which is the distance from the axis of rotation to our rectangle. Here's our rectangle, right? Imagine projecting it down. I told you this distance is always x, right? So x sub r here is just x, right? Because our axis of rotation is the y-axis. So x. What are the other 2 things that we need to know? Top function, bottom function. Top function here is, yeah, this big ugly thing. It's the red one, right? Negative x squared plus 3x. And then minus the bottom function, which is just x and then dx. But we do have something to resolve, right? Our limits of integration? It's not from 0 to 3, right? It's from 0 to wherever they hit each other, right? Well, I don't know. I have to solve it, don't I? I actually have to go figure that out. And I made this problem up, so there's no guarantee that this is going to be nice. But I'll go for it. All I have to do is set them equal to each other, right? And move things around. Subtract x on both sides. Oh, it's nice. Factor a negative x out. So 0 and 2. 0 and 2. So they start here, they hit, and they hit here at 2. So that means my top is 2. And then you'd finish it up. You'd distribute the x through, you'd integrate, and be happy. All right, well, the shells method is actually 7.3 in the book. 7.2 does not cover shells, but 7.3, if you look on our calendar, I don't think I forgot my folder, but 7.3 is not on our calendar of topics to cover. I just kind of squeeze it into 7.2. I don't know, some faculty don't cover shells. And so I go off their standard calendar.
How's that even possible?
It's, yeah, you just avoid giving problems that can't be done without it.
Yes.
Yeah.
So this is saying you don't need shells.
Yeah, I love shells. I think shells is fantastic. Plus, the whole way we generated the formula for shells is, I mean, that's kind of like the heart of what we're doing here, is coming up with these formulas. The homework assignment, though, for tonight, and I guess for the weekend, is page 378, problems 1 through 19 odd. You should be able to handle all those. 38 and 39 we haven't talked about yet. So we will come back next class. We will wrap up 7.2 by talking about these weird problems. And then we will start arc length and surface area. So how do you find, if you take a curve and, well, we'll talk about it next week. Arc length, surface area, applications, start chapter 8, and then we have a test at some point. Feel like I'm forgetting something. Have a good weekend, I guess.